Welcome to the lecture series on numerical methods, finite difference approach. In the last lecture, we have discussed this explicit scheme, and based on that we have solved one problem. And in the present lecture, we will start about implicit scheme, its compatibility, and afterwards we can just go for this convergence analysis and all other things. So, if you will just go for implicit method, so in the implicit method, first we will just discretize this equation. Suppose if the equation is in the form like del u by del t, this equals to del square u by del x square. Then we can just replace this derivative like at the point I j plus 1, such that time derivative is replaced by backward difference and space derivative is replaced by central difference. So, if you will just look at this earlier slides, so you can just find that in the explicit method especially we are just discretizing this differential equation at the mesh point I j there itself. But in the implicit method we are just going towards next iteration step in the time to visualize that what it is happening in the next cell. So, that is why we are just considering this mesh point at I j plus 1 cell, such that we can just consider this advanced cell considering this previous cycle calculation or the previous step calculation in that solution process. So, if you will just take this time derivative by a backward difference formulation and space derivative by a central difference approximation, then this del u by del t, it can be represented as u I j plus 1 minus u I j by del t. And if you will just go for this discretization of del square u by del x square term here by the central difference approximation at j plus 1 point. So, then we can just discretize this one in the form like u I minus 1 j plus 1 minus 2 u I j plus 1 plus u I plus 1 j plus 1 by del x square. And if you will just go for this order of convergence here, or this highest order of approximation, that we are just neglecting the terms, that is in the form of like first order terms we are just neglecting here for time, and second order approximation we are just considering for the central difference approximation here. And if you will just consider here r as in the form of like del t by del x whole square and neglecting the error terms, then we can just represent this system as a linear system of equation as minus r u I minus 1 j plus 1 plus 1 plus 2 r u I j plus 1 minus r u I plus 1 j plus 1, this equals to u I j here. Since u I j is known to us, if you will just look at the structure, you can just find that we are just moving I in the direction of x axis here, that is as starting as suppose like 0, 1, 2, and j is also starting from 0, 1, 2 likewise. And if we are just moving towards x direction, we are just taking the space length as del x here in each of these grid intervals, and if we are just moving in the time direction, we are just considering here each interval spacing as del t here. So, that is why if you will just consider this space direction at I jth level suppose, then we can just consider this as the j plus 1th level for time here, and we are just considering this calculation at the next time level or at t plus del t level. If we are just starting t equals to 0, then t1 equals to like t0 plus del t, that is nothing but del t there. In that level especially we are just signifying this grid as j plus 1th level there. So, that is why if we want to find out these values at the unknown level, we have to consider these values which should be known to us at the known level. So, that is why we are just considering u I j on the right hand side of this equation, since these values are known to us. So, if you will just go for like I equals to 1, 2 up to n minus 1, it will just furnish like n minus 1 set of equations in u I j plus 1 here, and these equations are solved for the values of u at each time level of j plus 1 there. So, this formula is known as Lasonins formula. And if you just see this molecule here, equation is in the form of like minus r u I minus 1 j plus 1 plus 1 plus 2 r u I j plus 1 minus r ui plus 1 j plus 1, this equals to uij here. So, if you will just see that this cell we are just formulating here at ith level and I plus 1th level and jth level and j plus 1th level, we can just see that first coefficient this is just taking as a minus r u I minus 1 j plus 1, and then 1 minus 2r means at j plus 1th level, if you will just see, this takes the coefficients of ui j plus 1 there. And if you will just see this last coefficient here, that is nothing but the coefficient of I plus 1 j plus 1 here. Since we are just considering these levels, this one as I plus 1 j plus 1 and this level as ij here, and this level as like I j plus 1 and this level as like I minus 1 j plus 1 here. So, all these coefficients, if you can just visualize the previous slide, you can just find that these are these coefficients associated throughout this equation. In Crank-Nicolson's method, this is like a average scale method, especially it is said to be. Since in the earlier method, if you will just go for explicit method, we are just considering these values at uij level, and in the next level we are just considering this implicit scheme, first one, that is in the form of like this computation is going at the node point that is at ij plus 1th level, and if you will just take the average of these two grid points level, that will just generate Crank-Nicolson's method here. The advantage of this Crank-Nicolson method is that here we are just considering both explicit and implicit scheme together. So, that is why this convergence will be more accurate compared to explicit scheme or implicit scheme there. So, in this method, especially as I have told that the difference is that the discretization equation is made at the midpoint of jth and j plus 1th levels, and both the time derivative and space derivative is replaced by central difference approximations here. Since the central difference approximations are gives the higher order convergence compared to the other methods or the compared to the other difference schemes. So, if you will just take del u by del t in a like central difference scheme here, since we are just discretizing this equation at the average point, that is at I j plus half here. So, that is why we can just take this one as a j plus half, since we are just considering like a neighborhood point of j plus half. So, that is why one side it will be j plus 1, other side it will be like j it will be present. So, that is why we can just consider this one as I j plus half minus ui j plus half minus half there. So, that is why this is just coming as this equation as like ui j plus 1 minus uij by del t. And if you will just take the average of the space derivative term in the right hand side, we can just find that this is nothing but the average of the central difference gives at ijth level and ij plus 1th level. So, if you will just take the central difference scheme of del square u by del x square at ijth level, we can just write this equation as in the form of ui minus 1j minus 2 uij plus ui plus 1j by del x square. And if you will just take this space derivative at ij plus 1 point, then we can just write this derivative term as ui minus 1 j plus 1 minus 2 ui j plus 1 plus ui plus 1 j plus 1 by del x square. And this order of approximation, if you will just see this central difference approximation for first order derivative, that is considered as the order of delta t here, and if you are just considering this order of approximation for central difference scheme, then we can just find that one as the order of del x square here. And as usual, as we have used in the earlier slides, so if you will just consider here r equals to del t by del x whole square and neglecting the error terms, then we can just rewrite the above equation as in the form like, since we are just evaluating at j plus 1th level values or the unknown level values we are just evaluating. So, that is why we can just keep the terms associated with j plus 1 terms in the left hand side, and the values which is known to us like jth level values, it can be kept on the right hand side of the equation. So, that is why we are just keeping these terms as minus r ui minus 1 j plus 1 plus 2 into 1 plus r ui j plus 1 minus r ui plus 1 j plus 1, this equals to r I minus 1 j plus 2 into 1 minus r. Since if you just see the coefficients here, we can just observe everything there. So, this equation set will vary from I equals to 1 to n. So, hence there will be n minus 1 equations with n minus 1 unknowns, and their solution will be solved at j plus 1th level. Since jth level all values are known to us or at the beginning of this calculation. So, these values will be taken from these boundary conditions and it can be implemented for the further calculations. So, if you just see this molecule of this Crank-Nicolson scheme here, we can just find that at j plus 1th level all the coefficients, they are just taken as like, if you just see here, r del t by del x square means we will have this coefficients here minus r, 2 into 1 plus r, this is minus r here. And if you just see like jth level calculation, we can just find this is as plus r here, 2 into 1 minus r here, r here. So, the same one, it is just written at jth level, it is just written as r, 2 into 1 minus r, and j plus 1th level, it is written as minus r, 2 into 1 plus r and minus r here. So, if you just go for this solution of this problem based on certain conditions that is prescribed initially, and these conditions are prescribed at the boundaries, then directly we can just obtain the solution. So, for this we have considered a practical example where the symmetricity is occurring at the center line, and the problem statement is written here as del u by del t equals to del square u by del x square, where x lies between 0 to 1 and time especially it is greater than 0 with the boundary conditions that is prescribed at x equals to 0 and at x equals to 1 as 1 here, and the initial condition that is just given as 1 plus 2x when x lies between 0 to half. If especially if you just see in a domain, if your boundary x boundary is starting at 0 and x boundary is ending at x equals to 1 here, and at jth level means we can just say that at t equals to 0 all these boundary conditions it has been prescribed to us, and along these boundaries this condition is also prescribed to us. If you just see here, u0 is especially it is considered as 1 here, and u1 is considered as 1 here also. And for this boundary, if you just see at t equals to 0, these values are given as 1 plus 2x. If at the end point, or if you just see at x equals to half, this is nothing but we are just getting as the value as 2 here. And if you will also come as x equals to half for this equation, we are just also getting this as a 2 here also. So, that is why there exists the symmetry at the center line of this equation here. So, the problem is symmetric about, we can just say, at x equals to 0.5 here, and subsequently we can just calculate this discretized domain at the first domain here and also in the last section of this domain. So, if you will just go for this calculation here, since del t is given as 0.08 here and r can be defined since del x is prescribed as 0.2. So, that is why we can just write r equals to del t by del x square, that is nothing but 0.08 by 0.04. So, the value is coming as 2 here, and if you just use this Crank-Nicolson scheme, then this scheme can be written as minus r ui minus 1 j plus 1 plus 2 into 1 plus r ui j plus 1 minus r ui plus 1 j plus 1. This equals to r ui minus 1 j plus 2 into 1 minus r ui j plus r ui plus 1 j. So, if you just put all these coefficients that is in the form of r here, that is as minus 2, then this will be 6, then this will be like minus 2, then this will be like 2, then 2 into 2 minus, sorry, 1 minus 2 here. So, that is why this is minus 2 is coming here. So, then this is 2 here. So, for or if we can just take common 2 from both the sides and cancel, then we can just obtain this equation in this form here. So, for I equals to 1, if you will just put, we are at the boundary, that is u0 j plus 1 plus 3 u1 j plus 1 minus u2 j plus 1, again we are at the boundary u0 j minus u1 j plus u2 j here. So, these boundary conditions, it is known from this given conditions, and that can be separated. So, for I equals to 2, if I will just put here, then this will just compute like the values minus u1 j plus 1 plus 3 u2 j plus 1 minus u3 j plus 1, this equals to u1 j minus u2 j plus u3 j here. Since already from the boundary conditions we can just use u0 j equals to u0 j plus 1, since it is along the first boundary there, so all values remain 1 there, and this implies that u2 j equals to u3 j, and which just impacts these equations as in the form like 3 u1 j plus 1 minus u2 j plus 1, this equals to 2 minus u1 j plus u2 j here, and we are just obtaining the second equation as in the form of minus u1 j plus 1 plus 2 u2 j plus 1, this equals to u1 j. So, if you will just go for this computation for different j values here, like j equals to 0, 1, 2 for different time levels, then we can just obtain this equation as a 3 u1 1 minus u2 1 as 2 minus u1 0 plus u2 0 here, and the second one we can just get from this as like minus u1 1 plus 2 u2 1, this equals to u1 0 here. And if you just separate this u1 1 term, that can be computed as 1.24 here and u2 1 as 1.32 here. Similarly, if you just put j equals to 1 here, then we can just find 3 u1 2 minus u2 2, this equals to 2 minus u1 1 plus u2 1, and the other one we can just get as minus u1 2 plus 2 u2 2, this equals to u1 1. If you will just solve together these two equations here, then we can just get u1 2 as 1.09 and u2 2 equals to 1.145 here. So, for j equals to 2, if you will just put, then we can just get these two equations are in the form like 3 u1 3 minus u2 3, this equals to 2 minus u1 2 plus u2 2 here, and the other equation is minus u1 3 plus 2 u2 3, this equals to u1 2, and if you just combine these two equations, then we can obtain the values as u1 3 equals to 1.04, u2 3 equals to 1.065 here. So, further if you just see that the values obtained in the explicit approach, especially that is just coming as 1.20 here and 1.325 for this case here. And if we are just going for this implicit approach, we are just obtaining these values as the scale as 1.24 here and 1.32 here. And similarly, at different levels we have just computed these values in the explicit approach, also in implicit approach, and the differences you can just find from this table here. Then we will just go for this compatibility, stability and convergence of these methods. Suppose if you are just representing u as the exact solution of the partial differential equation and ud is the exact solution of the discretized equation, since always we are just neglecting some higher order terms, that is why we are just writing that one as order of h, order of del x square or order of del t. So, this error, like if the exact value is different from this approximated value, we can just write this as the error term that is in the form of u minus ud. This is called the discretization error here. Assume this parabolic differential equation that is in the form of del u by del t equals to del square u by del x square, which is written as like x lies between 0 to L, t greater than 0, and let L is the operator which is defined as del by del t minus del square by del x square. And suppose this LT denotes the discretizing operator containing del x and del t as the parameters, and t is the truncation error here. Then we can just rewrite the above operator as in the form of like LU equals to 0, always we are just writing, that is nothing but the discretized solution plus the truncation error there. So, that is why we are just writing here LU equals to 0, that represents as the solution in the discretized operator form plus the truncation error. And especially we can just say that if UD is the exact solution of LDU equals to 0, if the discretization error u minus UD tends to 0 as del x and del t tends to 0, then UD is approaching towards u. That is, the finite difference solution is said to converge to the exact solution. So, if the finite difference approximation, that is LDU, tends to LU as del x and del t tends to 0 here, then t tends to 0 as del x and del t tends to 0, then the finite difference approximation is said to be compatible with the original ordinary differential equation or partial differential equation. So, while finding the solution for UD, so some errors like rounding and truncation error we are just associating in each of these equations. So, that may be in algebraic form or maybe in differential form, that is associated there. So, especially whenever we are just taking like finite difference form, always we will have like order of delta t or order of del x square or order of del x is present, and this will also keep on increasing whenever we are just moving for different steps there. So, the final solution will be different from this discretized solution at the earlier one, and if we can just find the final solution, it may be differed from UD and it can be called as UC here. Then this error associated with this propagation error, that is especially it can be written as UD minus UC, it is called the stability error, and if it tends to 0, then the finite difference scheme is said to be stable, and total error we can just write it as U minus UC, that is nothing but U minus UD plus UD minus UC. So, first we are just considering the discretization error, then this propagated error afterwards. And if you will just go for this compatibility of this explicit scheme for Taylor series expansion here, first we are just considering here del u by del t term. Since the equation is written especially in the form of like del u by del t equals to del square u by del x square. So, that is why if you will just consider this first term only del u by del t here, so this difference can be written in the form of u of x t plus del t minus u of x t by del t, that is nothing but del u by del t equals to del t by 2 del square u by del t square plus del square t del t whole square by 6 del q u by del t q plus del t q by 24, since it is 4 factorial del to the power 4 u by del t to the power 4 here. And if you will just take the central difference approximation, then this added truncation error, this is of this form here. And if you will just subtract these two terms, then we can just find that the discretized error or the truncation error are associated with this expansion here. If you will just write this truncation error, that is the difference of first this time expansion, that is nothing but minus of del t by 2 del square u by del x square, sorry del t square plus del t square by 6 del q u by del t q plus del t q by 24 del 4 u by del t to the power 4 plus up to rest of the terms. Since we are just taking difference and we are just taking to the left hand side, so that is why this term is positive here and this term is negative. And from this equation we can just conclude that t tends to 0 whenever del x and del t both tends to 0, since this is the multiplied factor, it is associated with both these terms here. Therefore, explicit scheme is compatible or consistent with this partial differential equation. And if you will just rewrite this equation 7.5 again, we can just find this difference as in the form of like minus del t by 2 del square u by del t square, and first associated term from this one, that is minus del x square by 12 del to the power 4 u by del x to the power 4. Then the second term, if I will just write here minus of del t square by 6 del q u by del t q minus del x q del to the power 6 u by 360 del x to the power 6. From this original partial differential equation, we have del by del t, since these operators can be written in equal form, since it is operated on the variable there, which gives del square by del t square as del to the power 4 by del x to the power 4, and del q by del t q, it is just giving you del to the power 6 by del x to the power 6. Since these are operators, especially we can just write f square equals to f into f there. So, that is why we have just represented in this form. And if you will just consider del t by del x square equals to r here, then equation 7.6 if you will just say here, then it can be reduced in the form like minus of del x square by 2 r minus 1 by 6 del square del to the power 4 u by del x to the power 4 minus del x to the power 4 by 6 into r square minus 1 by 60 del to the power 6 u by del x to the power 6 minus rest of the terms. If you will just consider r equals to 1 by 6 here, then this truncation error reduces to like minus of del to the power x 4 by 560 del 6 u by del x to the power 6 minus rest of the terms. For r equals to 1 by 6, the truncation error will be of highest order here. Thank you for listening this lecture.